In the last lecture, we derived the voltage and current expressions, then we defined the origin on the transmission line, we defined the origin at the load end, and then we defined all the distances on the transmission line measured from the load point towards the generator. That distance we denoted by variable L. So, we now have these voltages and currents which are given in terms of the lengths which are towards the generator from the load end, and then satisfying the boundary condition at the load end, we got the relationship between the impedance at the load end, which is related to a parameter which was the ratio of V minus by V plus. This quantity V minus by V plus is related to the energy reflected from the load end, and we defined this parameter, what is called the voltage reflection coefficient, which was the ratio of the reflected voltage to the incident voltage. Both these quantities are complex in nature, and that is the reason the reflection coefficient at any point on the transmission line is complex. Then at L equal to 0, that means at load end, the reflection coefficient, which is gamma at L equal to 0, that is equal to V minus upon V plus. So, the ratio of the reflected and the incident voltage at the load end is denoted by this quantity gamma at L equal to 0. Substituting this, we got the relationship between the load impedance and the reflection coefficient at the load end. If we now invert this relation, we will get the value of the reflection coefficient at the load end, and let us call that quantity as gamma L. So, this is the reflection coefficient at the load end, which is nothing but the gamma measured at L equal to 0, which is equal to ZL minus Z0 divided by ZL plus Z0. So, what we find here is that the reflection coefficient at the load end, which is a measure of how much energy is reflected from the load end, is related to the terminating impedance of the line, which is ZL. Also, it depends upon the characteristic impedance of the line. What we see from here, that since this quantity is equal to V minus divided by V plus, one thing immediately can strike to us is that when ZL is equal to Z0, that means if the terminating impedance on the line is equal to the characteristic impedance, the V minus upon V plus goes identically to 0. In other words, the reflection coefficient gamma L is equal to 0 when ZL is equal to Z0. So, we get here gamma L is equal to V minus upon V plus, that is equal to 0 when the load impedance is equal to the characteristic impedance. Now, this is a very interesting condition. What we see now is that if the load impedance is equal to the characteristic impedance, since this quantity is 0 and V plus will not be 0 because we have put some incident wave, so that means the V minus will be 0, or in other words, when the load impedance becomes equal to the characteristic impedance, there is no reflection on the line, and that is the condition we are looking for, because when we initially talked about the purpose of the transmission line, the objective was to transfer the power from the generator to the load. However, when we analyzed the transmission line, we found that there are some reflections on the transmission line and the entire energy is not transferred to the load. Now, we get a condition under which the entire energy will be transferred to the load, because there will not be any reflection on the line if the load impedance is equal to the characteristic impedance. So, the characteristic impedance is a very important parameter of the transmission line. One may wonder, where is this characteristic impedance located on transmission line? It is not located anywhere. It is a characteristic parameter which cannot be located on a transmission line, but it governs the power flow on transmission line. And this condition, that ZL equal to Z0, is what is called the match condition That means if the impedance is matched to the transmission line characteristic impedance, the power transfer is 100% and there is no reflected energy on the transmission line. This condition is similar to the maximum power transfer condition on the circuits, where if the load impedance is equal to the complex conjugate of the generator impedance, then there is a maximum power transfer from generator to the load. Exactly same condition is here for transmission line now, that when the load impedance is equal to the characteristic impedance of the line, the whole power gets transferred to the load and there is no reflected power on the transmission line. So, this condition we call as the matched load condition. One may then physically understand what is happening and why there is a reflection on the transmission line. Z0 represents some kind of a medium which is very smooth, on which the power is flowing along the transmission line. Suddenly it sees a disturbance on the transmission line in terms of impedance, because when it reaches to the other end of the transmission line, the impedance is no more seen equal to the same smooth flowing impedance, which is Z0. So, it is some kind of a step change which the energy flow encounters, and because of that part of the energy tends to get reflected on the transmission line. So, for maximum power transfer, our effort should be that the energy flow should always see an impedance which is equal to characteristic impedance. If any other impedance is kept other than characteristic impedance, there will always be reflection on transmission line and the power flow will not be maximum to the load. Having understood this now, then one can generalize this, and then one can say that the way we have defined the reflection coefficient at any point on transmission line, once you get the value of V minus upon V plus, I can find out the complex value of the reflection coefficient at any point on the transmission line. And once I define this parameter, which is the reflection coefficient, then I can substitute this quantity V minus upon V plus e to the power minus gamma upon e to the power plus gamma in our voltage and current relation, and we can define now the voltage and current at any point on transmission line in terms of the reflection coefficient. So, we get now the relation of the voltage and current, which is V as a function of length, that is equal to, as we had defined earlier, this quantity, the V was equal to V plus e to the power gamma L plus V minus e to the power minus gamma L. I can take V plus e to the power gamma L common. So, this quantity will become V minus upon V plus e to the power minus gamma L upon plus gamma L, that is nothing but the reflection coefficient at distance L. So, I get V L is equal to V plus e to the power gamma L into 1 plus reflection coefficient at L, and the current at that location will be V plus divided by Z naught e to the power gamma L 1 minus reflection coefficient at distance L. Once we get the voltage and current at any location, we can now find out what is the impedance at that location. So, we can divide this equation by this. So, we will get the impedance measured at a location L on the line, which is V at that location divided by current at that location. This will be equal to V plus e to the power gamma L will cancel. So, you will get Z naught into 1 plus gamma L divided by 1 minus gamma L. So, the impedance at any location on transmission line is related to the reflection coefficient at that location on the transmission line. Inverting the relation, we can get reflection coefficient at any point on the line, that is equal to Z at that location minus Z0 divided by Z at that location plus Z0. So, in fact, the impedance at any point on transmission line and the reflection coefficient at that location has 1-to-1 relationship. So, if I know the reflection coefficient at that location, I can find out what is the impedance at that point, and if I know what is the impedance at that point, I can calculate what is the reflection coefficient at that point. Once I get this, I can substitute for reflection coefficient gamma L, and noting that the quantity V minus upon V plus is the reflection coefficient at the load end, I can write down the impedance here in general form as follows. So, I can get now the impedance Z at any location L, that is equal to Z naught, gamma L, which is V minus upon V plus e to the power minus 2 gamma L. So, this is nothing but 1 plus gamma L e to the power minus 2 gamma L divided by 1 minus gamma L e to the power minus 2 gamma L. And gamma L is nothing but the reflection coefficient at the load end. So, gamma L, as we have already derived, is nothing but the load impedance minus Z0 divided by load impedance plus Z0. I can substitute for gamma L into this equation, and I can get a impedance at any point on the line in relation to the load impedance. So, I get a relation ZL, what is called the impedance transformation relation, that is equal to Z0 divided by 1 plus ZL minus Z0 divided by ZL plus Z0 e to the power minus 2 gamma L divided by 1 minus ZL minus Z0 divided by ZL plus Z0 e to the power minus 2 gamma L. Rearranging these terms and collecting the terms of ZL and Z0, separating them out, and noting that we are having now the terms which will be e to the power gamma L, I can rearrange and rewrite this expression in terms of the hyperbolic cosine and sine functions. So, this expression after resubstitution becomes ZL is equal to Z0 to ZL cos hyperbolic gamma L plus Z0 sin hyperbolic gamma L divided by Z0 cos hyperbolic gamma L plus ZL sin hyperbolic gamma L, where we have used a relation cos hyperbolic gamma L is equal to e to the power gamma L plus e to the power minus gamma L upon 2, and sin hyperbolic gamma L is equal to e to the power gamma L minus e to the power minus gamma L upon 2. So, this now is telling me that the impedance at location L is related to the load impedance through this relation, what as we call as the impedance transformation relation. So, this relation we call as the impedance transformation relation. And this relation is a very important relation in transmission line calculation, because what it tells you is that if a line is terminated in impedance which is equal to ZL, the impedance which you will measure at the input end of the line will not be ZL. It will be different than ZL, and not only it will be different than ZL, it will also depend upon the length of the line. So, for the same load which you have connected to the line, if the length of the line keeps varying, the impedance which you measure at the input of the line will keep varying. Or in other words, if I design a circuit at high frequencies and connect that circuit to a load, depending upon what piece of wire or cable I am connecting between the load and the circuit, the impedance seen by the circuit will be different. So, for the behavior of a circuit, the impedance seen by the circuit is more important. If that quantity keeps varying depending upon the length through which the actual impedance is connected to the circuit, the whole circuit behavior will keep on varying as a function of length of the connecting wire. When we go to high frequencies, even length of a connecting cable is important, because the impedance transformation which the cable does, it might change the impedances which are seen by the actual circuits which are connected to the end of the connecting cable. So, the important thing to note here is that whenever we are having distributed element, that is what whole thing we started with, then the impedance seen at input end of the transmission line will in general be different than the impedance connected to the load end of the transmission line, and the impedance transformation will essentially be done by that. One can also note important thing here, that I can take this Z naught down here, I can take Z naught common from denominator and numerator, and then it should be ZL, and then every quantity which I have here is now normalized with respect to Z naught. This quantity is ZL, Z of L divided by Z naught, this is ZL divided by Z naught, this is ZL divided by Z naught. So, the expression which I have for impedance transformation, this essentially can be written in terms of the normalized impedances. So, the same expression I can write down in terms of the normalized impedance, and let me define the normalized impedance by bar. So, any impedance which is normalized denoted by bar is equal to the actual impedance Z divided by the characteristic impedance. This is what is called the normalized impedance. So, by this token, then my ZL bar is equal to ZL divided by Z naught. Normalized impedance at any location L is equal to Z at that location L divided by Z naught, and so on. Substituting this in the impedance transformation relation which we derived here, I get the normalized impedances ZL, that is equal to ZL normalized cos hyperbolic gamma L plus sin hyperbolic gamma L divided by cos hyperbolic gamma L plus ZL normalized sin hyperbolic gamma L. So, the important thing is, on transmission line calculations, the absolute impedances do not mean anything. The impedances which are normalized with respect to the characteristic impedance has some meaning. What that means is, if I have a transmission line whose characteristic impedance is 50 ohms, a 100 ohm impedance is going to create the same reflection as if the transmission line was of characteristic impedance 300 ohms and the load impedance is of 600 ohms. So, the absolute impedance which you are connecting to the line has no meaning, and that is the reason before we start any transmission line calculation, first you ask what is the characteristic impedance of the line. Once you know the characteristic impedance, then every impedance which you have, you normalize those impedances with the characteristic impedance. So, every calculation which you do in transmission line is always in terms of the normalized impedances. As and when you require, you always undo the normalization and you find out the absolute impedances, but as far as the transmission line calculations are concerned, the impedance has to be always in terms of the normalized terms, and this normalization is with respect to the characteristic impedance. So, what we see is that the characteristic impedance which is not really located anywhere, which is not seen anywhere, which is always at the background, but is the governing parameter of the energy flow on transmission line. Because every calculation, every voltage current, whatever relationship we are talking about, they all are governed by this hidden parameter, which is what is called the characteristic impedance. So, characteristic impedance is an extremely important parameter, right, when we do the transmission line calculation. We also notice now from here that if the ZL is equal to Z0 or the normalized ZL is equal to 1, then this quantity is 1, this quantity is 1. Okay. So, this whole term will become equal to 1. So, normalized ZL will be equal to 1, or the absolute value of ZL will be equal to Z0. If Z normalized is equal to 1, that is ZL is equal to Z0, which we call as the match condition, then Z bar L at any location on the line which is equal to 1, that is the impedance measured at any point on the line will always be equal to the characteristic impedance. This is extremely important condition. What we are saying now is that if the load impedance is not equal to the characteristic impedance, then the impedance measured at any point on the line will be function of the length of the line, or the input impedance of the line is a function of length and the impedance which is connected to the other end of the line. However, if I take this special case, what is called the match condition, then load impedance is equal to Z0 and the impedance measured at every point on the line is equal to characteristic impedance. I do not have to worry about the length of the line now. The input impedance will always be equal to characteristic impedance no matter what is the length of the line. So, if the line is terminated in the characteristic impedance, then without worrying about the length of the line, I can carry out my measurements, because impedance seen at the other end of the line will always be equal to the characteristic impedance. So, the match condition is an extremely important condition, because it takes away all the worries which one would have because of the length of the line connecting between the load and the measurement point or the generator point. This also gives you now some means of providing this definition to the Z0. What we had done earlier, we had defined this characteristic parameter Z0, which had dimension of impedance. So, we started calling it characteristic impedance, because this impedance was related to the primary parameters of transmission line and the frequency. However, we did not have any physical way of defining this quantity. Now, maybe with this property of the match condition, we may give some physical meaning to the characteristic impedance. So, I can define now the characteristic impedance is that impedance with which if the line is terminated, then the impedance measured at any point on the line is equal to the terminating impedance. Let me repeat, characteristic impedance is that impedance with which if the line is terminated, the impedance measured on any point on the line is equal to that terminating impedance. That impedance then we call as the characteristic impedance. Sometimes we give another definition to the characteristic impedance, and that again comes from this condition, that when we have match condition, there is no reflected wave, and if there is no reflected wave, there is only incident wave going on transmission line, and we have seen earlier the incident wave always sees an impedance which is equal to characteristic impedance. If I take a hypothetical situation that the line is of infinite length, even if there was reflection on the other end of the line, it will take infinite time to reach to us. That means at any finite time, you will always see a wave which will be only the forward travelling wave or the incident wave. There will not be any reflected wave. So, the impedance measured on a line which is only now due to forward wave will be equal to the characteristic impedance. So, at times you also give a definition of characteristic impedance as it is the input impedance of a line of infinite length, because for that line the reflected wave would not have reached to you. So, the line sees always a forward travelling wave, and forward travelling wave always sees the impedance which is equal to characteristic impedance. So, the impedance measured at the input end of the line will be equal to the characteristic impedance. So, there are two ways to define the characteristic impedance. One is for an infinite line, other one is if the line is terminated in the characteristic impedance, then there is no reflection on the transmission line. With this now, we can now generalize the impedance transformation relationship. Up till now what we have done, we have transformed the impedance relation or the impedance which is at the load end at some distance L from the load end. One would then note here that there is nothing special about load end. The load end was coming because we defined the origin at load end. If we had defined the origin at somewhere else, we could have started measuring distances from that point and then would get an impedance transformation relationship with respect to that point which we call as the reference point. So, in fact, this relation is between any two points on transmission line for impedance transformation. So, if I know the impedance at any point on transmission line, I can find the impedance at any other point on the transmission line using this transformation relations. So, what we are saying now is, in general, if I have a transmission line which might be connected into some load, and if I measure at some location an impedance Z1, I am showing the arrow just to indicate that the generator is on the left side. So, energy flow is in this direction. If I go to any other location on transmission line, if I measure the impedance is equal to Z2, then I can use the impedance transformation relationship with this distance L, replacing load impedance ZL by Z1, and this ZL will indicate the impedance at this location 2. So, from the same impedance transformation relationship, I can write down here Z2 is equal to Z0 Z1 cos hyperbolic gamma L plus Z0 sin hyperbolic gamma L divided by Z0 cos hyperbolic gamma L plus Z1 sin hyperbolic gamma L. If I invert this relationship, that means if I find out the value of Z1 in terms of Z2, I will get Z1 is equal to Z0 Z2 cos hyperbolic gamma L minus Z0 sin hyperbolic gamma L divided by minus Z2, so this should be Z2 sin hyperbolic gamma. What has changed is, if I invert this relationship, I will get a negative sign here, I will get a negative sign here. This negative sign can be absorbed into the sin hyperbolic gamma L. So, this is equivalent to Z0 into sin hyperbolic gamma of minus L. Similarly, this quantity will become sin hyperbolic gamma of minus L. So, I have a Z1 related to Z2 with effectively L becoming negative, because cos hyperbolic minus L is equal to cos hyperbolic of gamma of plus L. So, this sign does not change. So, what we are now saying is that if I know the impedance at this location, I can use the impedance transformation relationship, which is this, to get an impedance at a distance L from this point towards the generator is on this side. However, the same relation can be used from transforming this impedance to this one with L replaced by minus L. And why? Because the distances which you have taken are taken positive towards the generator. So, if I transform the impedance from this point to this point, then I get a distance travelled towards the generator, which by definition is positive. However, if I transform the impedance from this location to this location, then I am moving away from the generator and the distance measured by definition is negative. So, the impedance transformation relation is the same relation, which is this. So, this relation which was same as this. So, in this case if I replace ZL by in general impedance at any location and measure the distances from that location, that L, if L is moved towards the generator, I take the distance L positive. If the L is moved towards the load or away from the generator, then I take this distance negative. So, I have to remember only one impedance transformation relation, which is this, and then I can transform the impedances from any point on the line to any other point on the line. And once I know the impedance, I can find out the reflection coefficient on that point of the line, because as we saw earlier, there is a unique relationship between the reflection coefficient and the impedance at any point on the transmission line. With this understanding of the impedance transformation and the definition of the characteristic impedance, now we can go to a little simplified version of this, and that is we discuss a special case of the general transmission line, what is called a low loss or a lossless transmission line. If you recall, the whole purpose of the transmission line was to transfer the power from the generator to the load effectively with as little power loss in between. That means ideally the structure, what is called transmission line, should be as low loss as possible. Therefore, in practice every effort is made to reduce the losses on the transmission line. So, if you take a good transmission line, its loss should be negligibly small at that operating frequency. Once I have that condition in practice, then one can make some simplifications in the analysis and come up with an idea of what is called a low loss transmission line, and if the losses are ideally 0 on a transmission line, then we call that transmission line as the lossless transmission line. Now, if you recall, the transmission line has 4 parameters, primary parameters. It was the resistance per unit length, the conductance per unit length, the capacitance per unit length, and the inductance per unit length. The ohmic elements in these 4 parameters are only the resistance and the conductance. That means the resistance of the 2 conductors of the line, they get heated because of ohmic losses, so they consume power. The dielectric, which is separating the 2 conductors of the transmission line, they have a leakage current, and again they have the ohmic losses, so they consume power. So, the power losing element in the transmission line are because of the resistance and the conductance. The inductance and capacitance, they store energy, but there is no loss in the inductance and capacitance. So, ideally a line will be lossless if the resistance and the conductance are identically 0. So, let us first write down the parameters for a ideal lossless transmission line, and then we will go to a more practical line, a good line, which is what is called a low loss transmission line, for which the losses are much smaller and there is a efficient power transfer from the generator to the load. So, taking the first case of what is called the lossless transmission line, by definition a line is called lossless if R is equal to 0 and G is equal to 0. Substituting R equal to 0 and G equal to 0 in the secondary constants of transmission line, that is the propagation constant gamma and the characteristic impedance, we get gamma is equal to square root of, now R is equal to 0, so this will be equal to j omega L multiplied by j omega C, that is equal to j omega square root LC. Now, by definition gamma was equal to alpha plus j beta, which this was the attenuation constant, this was the phase constant. So, this means for this case, lossless case, alpha is equal to 0 and beta is equal to omega square root LC. As correctly we can see here, if there are no losses, there is no reason for the wave amplitude to reduce on the transmission line. And as we know that alpha is the attenuation constant which gives you the reduction in the travelling wave amplitude as it travels on the transmission line. So, when alpha goes to 0, the wave amplitude does not reduce and there is a sustained propagation of a travelling wave on the transmission line. From here, omega, which is equal to 2 pi into frequency, and beta, as we have seen by definition, is 2 pi divided by lambda. We can substitute, so you get 2 pi divided by lambda, that is equal to 2 pi into frequency into square root of LC. From here 2 pi will cancel, so I get lambda into f, which is equal to 1 upon square root of LC. And from our basic physics we know frequency times the wavelength, that is nothing but the velocity of the wave, of the voltage wave on transmission line. So, the velocity of the wave is related to the inductance and capacitance per unit length on the transmission line. So, when the inductance and capacitances are given, the velocity of the wave on the transmission line is fixed. One may then wonder, I can arbitrarily choose the inductance and capacitances and can arbitrarily vary the velocity of the travelling wave on transmission line. In fact, the problem is not that. The situation is exactly opposite. The velocity is a parameter which is decided by the field distributions and the boundary condition, as we will see little later in this course. That means the inductances and capacitances of a transmission line are not independent, because this quantity V is decided by some other boundary conditions on the transmission lines. So, once the velocity of the travelling wave is fixed by some other conditions, this quantity is constant, or product of L and C is constant, and this one can see physically. If I consider the two conductors of transmission line, if I vary the separation between these two conductors, the mutual inductance is going to vary. So, the net inductance of the line is going to vary, but at the same time, since the separation between the conductor is varying, the capacitance also is going to vary. So, when I am trying to vary the inductance, the capacitance varies and vice versa. Precisely that is what we are talking about, that the inductance and capacitances per unit length on a transmission line are not independent quantities. The product of that is constant, because that is related to the velocity of the propagation of wave on the transmission line. So, for a lossless line, the velocity is given by 1 over square root LC, the alpha is identically 0. So, the wave has a phase constant beta, but its amplitude remains constant as it travels on the transmission line. For the lossless line, then we can calculate the another parameter, which is the characteristic impedance. Z0, and again substituting R equal to 0 and G is equal to 0, this will be equal to j omega L divided by j omega C, that is equal to square root of L C. So, the characteristic impedance of the line, the lossless line, is square root of the ratio of the inductance and capacitance per unit length. But the important thing to note now is that for a lossless line, this quantity is a real quantity. So, Z0 is real, and that is very interesting. Now, I do not have any resistance or conductance on the line. That means, I do not have any ohmic parameter on the line. R is 0, G is 0, but the characteristic impedance we do not know where it is somewhere on the transmission line. It governs the propagation of energy on the transmission line, and that quantity is a real quantity. So, I do not have any resistive element on the line, but the characteristic impedance is the real quantity. That means, the wave which travels, whether it is forward or backward, this always sees the characteristic impedance That means it sees an impedance which is equal to the real impedance, which is a resistive impedance. So, a forward travelling wave, when it travels on a lossless transmission line, it sees an impedance which is a real impedance like a resistance, and that makes sense physically, because once you are having a line which is having only forward wave, this wave is going to go and going to go forever, no energy is going to get reflected. That means this power somewhere is going to get dumped, and that is what this impedance Z naught is. So, if you are having a real quantity for the Z naught, that means now the power is completely transferred to the line. When you are saying power is transferred to the line, does not mean that the power is lost in the line. It is simply that the power has been carried by the line to the other end and no reflection has come back. So, for a lossless line, the characteristic impedance is a real quantity. That means if I measure now the input impedance of a line which is terminated into Z naught, I will see an impedance which will be like a resistance, and this line can extract power from a generator as if the power is drawn into a resistance. Once we get the feeling for now the lossless case, then one can now go to the more realistic lines where the losses are small, and then ask how much these parameters deviate, the beta or the propagation constant gamma and the Z naught, how much deviation is there between these parameters when the losses are relaxed. They are not ideally 0, but they are small. So, what one can do is one can now define more practical line, and that line we call as the low loss transmission line. And we define a low loss line as when R is much smaller compared to omega L. That means when the reactances are much larger compared to the resistances, then we call that line as the low loss transmission line. So, the condition that when R is much smaller compared to omega L and G is much smaller compared to omega C, if these conditions are satisfied, then we say this line is a low loss transmission line. Let us see what are the implications of this thing on the propagation parameters and the characteristic impedance. As we saw, this gamma is now square root of R plus J omega L into G plus J omega C. I can take J omega L and J omega C common from here. So, that is equal to J omega L to 1 minus J R upon omega L into J omega C 1 minus G upon omega C to the power half. Noting that R is much smaller compared to omega L and G is much smaller compared to omega C, and if I retain only the first order terms, the product of these will be second order term. So, if I retain only the first order term, this I can write as J omega L J omega C into 1 minus J R upon omega L minus J G upon omega C square root. This quantity I can take out, so that is equal to J omega square root L C 1 minus J R upon omega L minus J G upon omega C to the power half. Again, expanding this the binomial series and retaining only the first order term, this can be approximated as the gamma is equal to j omega square root L C 1 minus j r upon 2 omega L minus j g upon 2 omega c. Taking this inside, this can be written as j omega square root L C plus, you take it inside, omega will cancel with this, square root L will cancel with this. So, this will be equal to 1 upon 2 r square root c by L plus g upon 2 square root L by c. So, this quantity here, which is the imaginary part of the propagation constant, that represents beta, and this quantity here represents the attenuation constant alpha. Look at what we had got for the lossless transmission line. When we had a lossless transmission line, when r was equal to 0, g equal to 0, we had alpha equal to 0 and we had beta, which was omega square root L C. In this case also, when we are having low loss, the beta is still omega square root L C. That means the phase constant to the first order does not change when we introduce a small loss in the transmission line. That means, if I am interested only the phase calculations on transmission line, then the line can be treated like a lossless line, because beta value does not change, and I can carry out the analysis of transmission line for a low loss transmission line same as if there was no loss on the transmission line, and the line is the ideal line with r equal to 0, g equal to 0. However, in case of a real line, even with a small loss, you have this value alpha, which is related to r and g. So, where the wave travels, the amplitude reduces slowly as it travels on this transmission line, but the amplitude does not vary rapidly. There is a small decrease in the amplitude. So, over a short distance, if I do the calculations, the line can still be treated like a lossless line with the phase constant, which is equal to omega square root L C. If I look at this quantity here, which is square root C by L or square root L by C, this is nothing but the characteristic impedance of the line, which was lossless. So, if I say that my losses are very small, I can substitute for square root L by C is equal to Z naught. So, this quantity can also be written as omega square root L C plus 1 upon 2, this is R divided by Z naught plus G into Z naught. So, for the quick calculation, if I know the resistance per unit length, if I know the conductance per unit length, and if I know the characteristic impedance of the line, okay, I can calculate what is the phase constant, which is same as the lossless line, and I can calculate the small, but whatever the value of the attenuation constant is from this expression. So, for a real line, one can calculate the value of alpha and beta, and then one can proceed for the calculation of the impedance and other things on the transmission line. As we have done now the calculation for gamma, we can write now the characteristic impedance for the low loss line Z0, that is equal to R plus j omega L divided by G plus j omega C. Again doing the same thing, taking the j omega L and j omega C common from these parameters, this you can write as square root of j omega L into 1 minus j r upon omega L j omega C 1 minus j g upon omega C. this quantity square root L upon C, that will be nothing but the characteristic impedance of the ideal transmission line. I can expand these parameters again, and this we can write as square root L upon C. This square root, again, since r by omega L is very small, this can be approximated by 1 minus r upon 2 omega L. This will be 1 minus g upon 2 omega C. I can bring this to the denominator and then approximate it to write as 1 minus j r upon 2 omega L plus g upon 2 omega C. So, the characteristic impedance, this quantity is real, square root L by C, which is nothing but the characteristic impedance of the lossless transmission line. But now for a real low loss line, the characteristic impedance is no more real. It has a component which is imaginary, which is coming from this quantity. There is some j here. So, we conclude now two important things, that for a low loss transmission line, the propagation constant gamma has two parts. It has imaginary part and it has the real part. The imaginary part, which is nothing but the phase constant, that is same as the phase constant of a lossless transmission line. However, the attenuation constant has a small value. The characteristic impedance of a low loss transmission line is no more real, it is complex. Its real value is almost same as the characteristic impedance of a lossless transmission line, but now you are having a small imaginary part which represents the losses in the transmission line. With this understanding now of the propagation constant and the characteristic impedance of the low loss transmission line, now here onwards, until and unless specifically we are told to include the losses in the transmission line, we assume the line to be lossless and carry out the analysis of the impedances, voltages, currents and all other things under the assumption that there are no losses on the transmission line. So, in the next lecture and onwards, we will in detail discuss the behavior and the analysis of the lossless transmission lines.